All right, today we're going to talk through some binary relations examples, so specifically determining if a relation is reflexive, symmetric, and or transitive. So we have three different relations here. Let's start with number one. So number one says determine if the relation R on the set A, which is the set of numbers 1 and 2, given by R equals the set of ordered pairs 1, 2, and 2, 1 is reflexive. All right, now this example is a little bit different than the ones in the notes, but remember that we define a relation R on a set A. So here our set is just containing those two numbers, and it's supposed to be a subset of A cross A, or the Cartesian product of A with A. So this is our relation, and it's just given to us. These are the only two ordered pairs in that relation. Okay. So let's remember what it means to be reflexive. Reflexive means that if A is an arbitrary element of our set capital A, then the ordered pair A comma A is in the relation. So we want to ask ourselves, is that the case for this relation? In other words, for every element in this set, is that number with itself in the relation? And hopefully the answer that you're thinking is that it's not reflexive. And we would say that's because 1 is an element of the set A, but the ordered pair 1, 1 is not an element of our relation. That's also true for 2, right? The ordered pair 2, 2 is not an element of our relation, so that means that that relation is definitely not reflexive. All right, moving on to our next example. Let's see, so we have this relation on the set of natural numbers given by our relation is a set of ordered pairs AB such that A is not equal to B, and we want to know whether or not that relation is symmetric. Okay, so what does symmetric mean? All right, symmetric means that if we have an ordered pair that looks like AB is an element of the relation, then when we switch those to make it B comma A, that's also an element of the relation. So here we're trying to ask ourselves, is that true? So let's suppose that we have just arbitrary natural numbers, A and B, such that A comma B is in the relation. Well, what does that mean? Well, that tells us that it fits this criteria. A does not equal to B, okay? So we have two numbers, A and B. They are not equal to each other. Well, obviously, if A is not equal to B, then that also means that B is not equal to A. And when we write it this way, if B is not equal to A, then that tells us the ordered pair B comma A is in the relation. So notice that we did this with arbitrary elements, A and B. I'm not choosing specific numbers, but rather trying to argue the case in general. So we started with this, that AB is in the relation, and then mathematically we're showing that B comma A is also in the relation, and that means that this relation is symmetric. All right. Our last example is looking at a relation to see if it's transitive. So here we have a binary relation on the set of integers. So remember, integers, we're thinking positives and negatives. And this relation is ordered pairs A comma B, such that when you do A divided by B, you get an integer. Okay, and we want to know if this relation is transitive. All right, so what does transitive mean again? Okay, transitive. So for transitive, we have a lot going on. Actually, we start with 3 elements that are in our set. So we're just going to call them A, B, and C, because again, we don't want to talk about specific elements. We want to talk about it in the general case. So if we have 3 elements, A, B, and C, and we're also assuming that A comma B is in the relation and B comma C is in the relation, I guess. And then it will be transitive if we're assuming all those things then if we can somehow reason that A comma C is also in the relation, then that would mean that it's transitive. Whew, that's a lot. All right, so what are we doing here? We get to suppose, in trying to show that it's transitive, that we have three integers, A, B, and C. Again, we don't know what they are. And that A comma B is in the relation and B comma C is in the relation. Okay, so now it's helpful to think about what does it mean to actually be in the relation. That means it fits our definition up here. Or in other words, when you do the first number divided by the second number, the answer is actually an integer. All right, so, woo, the wrong button. All right, so then we know that A divided by B is an integer, and since this ordered pair is also in the relation, we can say that B divided by C is an integer, or that it exists in the relation. Whoops, where's my eraser? All right. There we go. All right, so we have A divided by B, whatever that is an integer, and B divided by C is an integer. All right, and what we want to know is this final part of the definition of transitive, is that satisfied? Well, A comma C being in the relation in this case means that A divided by C is an integer. All right, well, how do we get there just knowing some stuff about A divided by B and B divided by C? Well, one thing that we could do is A divided by B times B divided by C. And the reason that we want to do that is for two reasons. So this number multiplied by this number, if we multiply two integers, we're going to get an integer. We say the integers are closed under multiplication. But the other reason that we want to do that is because if we have A divided by B times B divided by C, then our B's cancel out and we're left with A divided by C. So keep in mind that these two are both integers. And again, when we multiply two integers together, we're going to get another something that is an integer. So if A divided by C is an integer, what does that mean? That means that the ordered pair A comma C is an element of our relation. Whew, okay, that's a lot. So remember, we're assuming that we had three integers where A and B were in the relation and B and C were in the relation, and we were able to show that that implies that A comma C is in the relation, and thus we can say that R is transitive.